In software development, there are two primary ways to build complex systems. While many beginners gravitate toward inheritance, where a new class takes on the properties of a parent class, there is a more flexible approach known as composition. Composition is the practice of building complex objects by containing other, smaller objects inside them. Instead of a class saying, I am a version of that, it says, I own these specialist tools and I will ask them to do the work for me. This design philosophy is summed up in a standard rule used by senior engineers, which you can see perfectly illustrated here. Favor composition over inheritance. Notice how the composition side outweighs inheritance on this balance scale. To understand why we prefer this, let's consider the difference between sculpting with clay and building with Lego. Inheritance is like clay. You start with a large block, your parent class, and you carve your specific shape out of it, like shaping this dog. However, this creates a rigid dependency. If the original block of clay has a hidden crack, every single sculpture you carve from it will inherit that exact same flaw. If you want to change the base material, you have to redo every sculpture from scratch. Composition is like Lego. Instead of one solid block, you have independent bricks. If you are building a car, you have an engine brick, a gearbox brick, and a chassis brick. You assemble them to make your final car. The beauty of this is that if a more efficient engine is invented, you don't have to rebuild the entire car. You simply swap out the engine brick. The rest of the car remains completely untouched and functional. So how do you decide which approach to use in your code? You can apply a simple mental framework called the is a, has a test. Let's look at this table to break down the logic. In the first row, we ask ourselves, is A a type of B? If the answer is yes, like a dog is an animal, then inheritance is appropriate. The dog intrinsically belongs to the category of animals. In the second row, we ask, does A own or use B? If the answer is yes, like a car has an engine, then we use composition. The car is not a type of engine. It simply contains an engine to function. You can even see this mapped out on this real-world robot car here, composed of dozens of independent modules. The core takeaway is Favour composition creates systems built from independent, swappable parts rather than rigid, fragile hierarchies. Now let's explore how this swappable nature of composition gives us massive advantages when our code is actually running. Following our discussion on building complex systems, choosing composition over inheritance offers several major advantages that make your code much more flexible. First, it allows you to swap components at runtime. Look at this car here on the left. If you use composition, you can literally pull out engine V1 and drop in engine V2 while the program is actually running, completely changing the car's behavior on the fly. Second, it prevents what we call deep inheritance chains. When you have a long, rigid chain of classes, a minor change at the very top can ripple all the way down, breaking dozens of subclasses below it. Third, because each component is independent, you can test each part thoroughly. You can test the engine, the gearbox, and the battery completely separately to ensure they work perfectly before ever putting them together. Finally, it keeps your code focused and clean. Each class only handles its specific single responsibility, whether that's handling power, transmission, or comfort. To really see the danger of getting inheritance wrong, let's focus on this top left section labeled Inheritance Gone Wrong. We see a classic fragile base class problem. A vehicle becomes a car, which becomes an electric car, then an electric sports car. It just keeps going deeper. If you change a fundamental property up here in the vehicle class, every single specific model below it might break entirely. But now, look right below that at composition done right. Here the car class is just a simple container. It just holds an engine object, a gearbox object, a battery, and a sunroof.
If you want to change the engine, you only change the engine class, and the car itself remains completely untouched. This is exactly how real-world manufacturing works at companies like Mahindra or Maruti Suzuki. As shown in the center, a vehicle is not an engine. Instead, it simply has an engine and has a gearbox. When an engineer decides to switch a specific car model from a petrol engine to a hybrid engine, components like the gearbox, chassis, and safety system remain completely untouched. In a deep inheritance structure over here on the right, that same exact change would force a massive rewrite across 6 different levels of code. But with the composition tree, a change in the engine only affects the engine class. Modern financial systems use this exact same modular logic. Look down here at how a payment processor like Stripe handles a charge. A charge object doesn't try to inherit the properties of a person or a currency. Instead, it acts as a container that holds a customer, a payment method, a currency, and a risk score. When Stripe needs to add a brand new payment method such as UPI, they don't have to rewrite their core charge logic. They simply create a new UPI class and plug it right into the charge container. Because of this setup, there is zero ripple effect. The customer, currency, and charge logic remain perfectly untouched and safe. This incredible modularity is the core power of composition, allowing systems to grow safely and cleanly. Let's look at how this is implemented in actual Python code for an e-commerce system next.
Let's look at how this composition concept is actually implemented in Python code, starting with an e-commerce system like Amazon or Flipkart. We start by building what we call component classes. Think of these as small independent specialists. First up, we have the customer class, which handles identity. It stores an ID, name, email, and phone number. It has one simple job: knowing who the person is. Next, the address class handles location. It doesn't care who the customer is. It just knows how to store the street, city, and PIN code. And importantly, how to format a mailing address. Third, the PaymentInfo class handles the transaction details, like whether the user used a credit card or UPI. And fourth, the OrderItem class handles the specific product being bought. It keeps track of the price and the quantity. Notice it includes a method called line total, which simply multiplies the unit price by the quantity to calculate the cost for that specific item. Once we have these independent parts, we build our composite class called order. Notice that order does not inherit from anything. Instead, it takes a customer, an address, and payment info and stores them as its own properties. This is a classic has-a relationship. The order class then delegates the heavy lifting. When it needs to print an invoice, it doesn't try to figure out how to format an address itself. It simply delegates the task, calling format address on its delivery address component. It asks the specialist object to do the work. To calculate the subtotal, it acts as a coordinator, summing up the line total of every order item in its list. Then, to calculate the tax, it uses a higher level logic, taking that subtotal and multiplying it by 0.18, which represents an 18% GST rate. This shows exactly how the composite class uses the data from its components to perform its own logic. Because of this modular structure, if a customer updates their delivery address, we don't need to destroy and recreate the entire order object. We just swap the old address object for a new one in one line of code. Now, to apply these concepts to another domain, consider building a patient management system for a hospital. Just like before, you begin by creating independent component classes, shown down here. These include a doctor class for medical staff, an insurance info class that includes a handy method to check if a treatment is covered, a medical record class to track allergies and conditions, and an appointment class for scheduling. Then you create your composite class, called patient. This class contains all the other objects. It has an insurance object, a medical record, a list of appointments, and a list of doctors. Looking at the methods for the patient class on the right, the add appointment method links a doctor to a time slot. The getTotalBill method acts as a coordinator, summing up the consultation fees from all the doctor objects the patient has seen. And the printPatientSummary method delegates the formatting tasks to the individual components, ensuring the output is clean. You can see these structures in the code blocks below, where we define our component classes,
assemble them in our composite patient class, and finally implement the coordinating methods. This modular approach keeps your code flexible and easy to maintain. Next, we will summarize these principles into 3 golden rules to help you decide when to use composition.
To bring everything we've covered together, let's review our 3 golden rules. First is the is-a versus has-a test. When deciding how to relate objects, ask yourself a simple question. Is the new object a specific variation of an existing one? If an animal is a dog, use inheritance. But if your object is made up of other distinct parts, like how a car has an engine, wheels, and steering, you definitely want to use composition. Our second rule is about swapping at runtime. Look at what happens with composition. If you need a different engine while the program is running, it takes just one simple line of code to swap it out dynamically. On the flip side, modifying a deep inheritance tree often creates a ripple effect, where changing one parent class forces you to rewrite or fix large chunks of the rest of the system. Rule 3 is delegation. Your main classes shouldn't be giant, complex files trying to handle all the logic themselves. Instead, let an order class delegate to a customer object for identity, to an address object for location, and to a PaymentInfo object for billing. Each component acts as an independent expert in its own little domain. This is exactly how hardware engineers build complex systems like this Raspberry Pi computer. They don't cast the whole board from a single rigid piece of silicon. They plug in USB ports, attach Ethernet ports, and integrate individual parts to make the whole system function. Software should be built exactly the same way, with parts. So here is your professional rule of thumb. Always start your projects using composition. As your system evolves, if a true parent-child relationship emerges, you can always convert that specific part to inheritance later. But you should absolutely avoid creating massive, tangled inheritance chains right out of the gate. Trying to break those apart after a project is built is one of the most painful, difficult tasks in software engineering. By treating your objects as independent, delegating experts, your code will remain incredibly flexible, easily testable, and a breeze to maintain as your application scales.